through it like really quickly, and if you want me to stop, then just stop me, okay? So the most important part, like in the chapter 4, I think it's the first step. It will be the free body diagram stuff. So I think you guys maybe can master it, right? Yeah? So from chapter 1, this is the 2D and 3D problems about when we're talking about static equilibrium. So like for 2D problems, you make sure the x-axis and y-axis, the force on it will be 0, and like the moment is also 0, so some sort of this. So if you do this like correctly, you will make the free body diagram correctly. So this is an example from a textbook. I think you guys can pretty much do this, right? Yeah, so I'll skip this. And this is like showing how to do the free body diagram. So, do you guys need me to like write some steps for you, or it's fine for you guys? Okay? Everybody okay? So this is like how we do the free body diagram. So that's another example for this. Then the normal stress and strain. This is the most important part. This will like affect the chapter 2 a lot, since we are talking about like deflection, strain, stress, force. So the stress is defined by force in per square in per area, and strain is like elongation over the total length. So keep in mind, when we are talking the strain in this course, is we are talking about the engineering strain. What is it? Is it because when we are in the real world, the length will definitely be affected, and it will totally like different from the original strength, original length. So when we are talking in this course, we are talking about like the strain versus the original strength or original area. So I think you are doing this stuff, right? Like where we can find what's that? What's that? Centroid, right? Centroid. So everyone is familiar with this, right? How you can find the centroid, like according to X or according to Y. So basically, it's the concept of like multiplying like the distance and the area, like you sum up like all of them and divide it by the total area. So you can get where is the centroid. So this is an example like we will talk about in like maybe chapter 2. So it's not important. Yeah, this is talking about like how we can calculate the stress like in certain area. So I think you have go through this kind of examples during the class, right? So like first you calculate the area and considering the free body diagram, and once you get the force and you divide it by the area, and you get the stress. And the strain part is like once you got the elongation and you divide it by the total strength, total length, and you get the strain. And one thing you have to keep in mind is that the units, you have to make sure the units are all the same, especially you're doing calculated strain. So if you're in the micrometers scale, and you just have to make sure all of the calculation is in the micrometer scale. So, and this is a tensile test machine, but I'm not really sure you will get getting like exam for contents like what we will do the experiment or not. So this is a stress strain curve. So I believe Professor Wu have talking about this curve. So I've talked about the true strain. So this part is where the true strain stands for. It's like this part is the engineering strain. I mean, stress versus engineering strain. So do you guys know the difference between the strain hardening and strain softening? No? So this part, this curve right here is the strain hardening. Like you can it will increase the strain the stress like by holding the same strain, and the strain softening is a different way around, right? So this part from C to D is the strain hardening, and to D to E is the strain softening. So nothing important here. And the Hooke's law. This is one of the important part in this course. So the strain equals Young's modulus times stress equals the Young's modulus times strain. So this is the basic knowledge of Hooke's law. It's basically times a certain constant to the strain, and you will get the stress. So Poisson ratio is defined by the lateral strain over the axial strain. So once you got the lateral strain, you divide it by the axial strain, and you'll get the Poisson ratio. And don't forget, there's a definition of the Poisson ratio, so you have to add the symbol. And shear. Shear is like similar to stress. It's the it's shear divided by area equals to shear stress. So are we on the same page? I think if you if like in the final exam, if there's talking about the torque, then you will be more familiar to shear stress. So there's also Hooke's law, like the shear strain equals G, the shear modulus, times to the shear strength. And the shear modulus, we can get it like we will get like Young's modulus divided by 2 times 1 plus Poisson ratio. Then we can calculate the shear modulus. So this is some examples for calculating the strain, stress, and area stuff. Everyone is okay? Just go through. Chapter 1. So for chapter 1, are you guys doing okay for like no matter the assignments or quiz? Are you guys fine? No?
Since like we are learning this course at the same time with static and applied mechanics, that's the big problem.
But I think that's like you mean static rock mechanics? Rock or force? The other course is what?
This course we are taking this course in the same time with static or applied mechanics.
Ah, okay, I see. But it will definitely help you to draw the free body diagram, right?
Yeah.
Yeah. So this is chapter 1. We already finished the reviewing step, okay? Chapter 2. Okay, we are talking about chapter 2, the axial loading members. So it's basically to help us to calculate the elongation of the rod or some springs. So there's a definition of what is stiffness. It's basically the P over delta, and just keep in mind that is some definition about stiffness and flexibility. So you have to be careful since stiffness and flexibility are really similar, but it's in opposite way, right? So when we are talking about the prismatic bars, first I would like to having a little introduce about this equation right here, delta equals PL over EA. So basically it's based on the Hooke's law. Like the stress equals the Young's modulus times strain, and when we define the stress, it is the force over area, and the strain is the elongation over the length. So when we substitute this stress and strain into the equation, we can get the delta equals P over EA. So this equation is like the basic concept of chapter 2. So if you forget this equation, you don't need to take the test. You don't have to take the test because you will lose like every point in chapter 2. So please remember this. It's very important. And one more thing is that this is really important to define like what is positive and what is negative. So I believe this is from the textbook. For this kind of definition, we define positive when the elongation happens, and we define negative when it is the rod is shortening. So when you calculate the answer when it is shows like it's negative, and it means that the rod is shortening. So I think the definition part, I would recommend you guys to memorize that, or you will have to like to remember your own definition. And so when you are like having the answers, you will know it's like no matter it is elongation or shortening. So do you guys know there's like 3 types of questions? Like 3 or 2 types? So this is the one like all the different segments, like lining lines. There's another one, looks like here. There's these kinds of questions, right? Yeah. The parallel one. You guys know this kind of question? Haven't? So, so for these kind of questions, you can see the elongation values. We have to add up like each segments, and we get the overall elongation. And for these kinds of questions, they will have the same elongation. Yeah, that's right? So, anyone has some questions? So, if we categorize the type of the questions into several types, so once we see it is like categorized 1, categorized 2, so we will immediately reflect like how we will do the exam, right? So for these kind of questions, this is, I will say, it's like the string. Let's go. I forgot about it. When we like hang the rods like with different materials together, in these kind of questions, you have to sum up like all of the segments elongation, right? And this is like another same question, but within different directions. So the basic idea is to follow the general elongation equation, like PL over EA, and we sum it up. And we come up these kind of questions, right? Like the shape or the volume, it will differ from the length, right? So this is basically the same concept. We didn't change any concept. So the idea is like we write the force or the area into functions, and we integrate it. So after the integration, we'll get the sum of elongation. Everyone's okay? Yeah. So you guys know how to draw the axial force diagram and axial displacement diagram? No one? Yeah.
For chapter 459, do we need to understand beforehand of chapter 1 and 2?
Chapter 1, yes, but chapter 2, a little.
Okay, so I think some of us are still struggling with chapter 1 and 2. So maybe if we finish chapter 4 first, and then if possible we can go back to chapter 1 and do some example questions.
Yeah. So is it okay I skip like rest of the chapter 2? Or I will go through it really fast.
Skip chapter 2 and go to chapter 4, then review chapter 1 and 2.
Yeah.
I think I'll finish it in 15 minutes. So
Okay.
So this is a force diagram, and this is the displacement diagram. So I think this is really similar to the shear diagram and the moment diagram. So do you guys know the difference between the statically determinate and the statically indeterminate? You guys know?
just a different amount of the unknown equation, right? For the intermediate is more than 3, but the intermediate is just 3, right?
Yeah. So, with if you like, with dealing with the indeterminate question stuff, you have to see, or you have to like somehow write the equation of compatibility. Hard to pronounce.
Compatibility.
And this kind of question is like the elongation between AB is equals to 0. So if you write like delta AC added by delta CB and calculate like different elongation, and you know like what is the reaction force in A and reaction force in B. And this is, I think you will have to know, this is like a basic. So, I mean the stresses or the force on inclined sections. So everyone knows how to calculate, right? If you don't know, please raise your hand. I will show how to calculate it. Okay. So you can see, this is where P headed, right? And this is the, I would say the normal way, like go vertically to the plane, right? Then this is the horizontal way to this plane, right? So once we got, there's like this angle, right? Turning, it's like counterclockwise, right? Theta. So by this rectangular, we can see when we are calculating for like, for instance, we just times like cosine theta, because theta means like this is perpendicular, right? And this is theta. So
90.
So when we are calculating this, this is also perpendicular. So this basically means 8. So cosine theta equals OB over OA, right? Cosine theta. So if you are calculating this in the triangle, so it will be P times right? Because in this triangle, we have to
Jason divided by
divide the force into
horizontal.
normal and shear, right? Yeah, so when this is perpendicular, this is theta. So the V equals P times sine theta. Okay? You know what I'm saying? But I think you guys can do this well, but I think the most important part of the trick is how to draw this, right? How to draw this, because once I've done this drawing, everyone can calculate where's the normal and where's the shear. So you have to really somehow memorize a little about how we will be drawing this kind of rectangle or triangle. So we talk about this. So when we talk about this kind of stress, do you guys know why it is A over cosine theta? Do you know why? No? So this is the A cross section. This is the A inclined place. So by dividing, sorry, right here. So A cross, this is like A, B, C. A, B, okay? Sounds, you can see this like slightly different from the last triangle, right? So what is no, I write it wrong. No. Like this. Yeah, this is wrong. So it will equals A cross divided by cosine theta. So you guys will have to remember like at least some of the equations, like the inclined plane, the cross section, the inclined section. So strain energy, I'll skip this, or because or I can go through this. It's like the force times the elongation will equals the energy, the work, right? So the strain energy is defined as the energy absorbed by the bar during the loading. So it's like P times the total elongation. And in this chapter, the strain energy part will definitely affect like in chapter 10 or 9. So I think you guys will have to somehow remember or have some sort of knowledge in the strain energy part. Yeah, and let's chapter 2. Let's start chapter 4. So far so good? Everybody's okay? Okay, so for the shear force and bending moments, I think it, in your lectures, it focuses on the shear moment diagram, right? So, do you guys know how to draw a shear moment diagram? Everyone knows it?
No.
No?
Is there like
Yeah.
a pathway to draw the shear moment
Yeah,
diagram?
that's why I'm here.
No, but I think like I struggle most with choosing which cross section
Yes,
to like
choosing
choose,
cross
you know.
section.
Ah, I see. I mean, there's like multiple ways of drawing the shear moment diagram, right?
Yeah.
I'm not telling you how, I'm not teaching you how to draw by the function today. You know there's a way to draw by the function, right? It's like, it's, I don't think it's really effective to teach you guys how to draw by function because you have to integrate like the shear to moment and integrate the force to the shear. Yeah, it's from where is it? Yeah, here. Yeah, this one. If you know like the function of the force, like the distributed loading, and you can get the shear by integrate length and get the moment by integrate the shear, right? Are we on the same page? This is another way, I mean, this is a theoretical way to draw a shear moment diagram. But it is really, I mean, it is hard for the new learners to define a proper way to like find out what is the equation or what is the function of the, no matter the distributed load, the constraint load. So in today's tutor, I'll teach you guys a fast way to draw it, but I don't think you can use it like in every situation. So you will have to at least know the basic concept about how to draw it. So when you find out that my ways are not really useful, you can like at least get some scores from the basic concept, right? So we'll start from the theoretical concept. So what is there's like different types of beam, and it will definitely affect the answer of your free body diagram and the shear or moment diagram. So when we're talking about simple beam, it contains a pin and a roller. So you guys know the difference from the pin and the roller, right? One constrains vertical direction and one constrains the horizontal and vertical direction. Okay? And cantilever beam. Cantilever. How to pronounce it?
Cantilever.
Cantilever?
Cantilever.
Yeah. So this kind of beam is fixed at the end and with other free without any support. So in these three types of beams, you will have to at least know how to draw the reaction force. So for instance, in the cantilever beam type, beside the horizontal reaction force, the vertical reaction force, there's a moment. You have to consider a moment in, right? And for a simple beam, there's no moment in the hinge or roller. And for the overhanging beam, you will have to consider there's like moment in the overhanging part, right? One more thing, it's like, so we talk about how to calculate the incline force, right? So in chapter 4, there's like chances you'll get the force like P1. So you have to distribute the P1 into horizontal and vertical and calculate the free body diagram. So in this case, the P1's horizontal component is, anyone know?
Px and Py.
Yeah, so how to calculate Px and Py? Px
P
equals,
is equals to square root of the Px squared plus Py squared. That's the result.
yeah, you can say that, but I mean, Px equals P1 times
Cosine and sine theta.
cosine alpha, right? So, there's like different release when it means that there's like different boundary condition when we are talking about this kind of question. So, like in this graph, when you are drawing this, and you're seeing this kind of graph in the exams, this means the axial release. I believe it will be also in the description, like in the quiz or in the midterm exam. So the axial release means that there's the vertical or the normal stress equals to 0, and shear and moment are not 0. It means there's no axial force. And the torque release is the same concept. The torque equals to 0, but the axial loading, the shear, the moment are 0. So there's like 4 of them, including axial release, torque release, shear release, and moment release. So you have to keep in mind, when we are talking about this kind of release, it will be a boundary condition that will help you to, no matter calculating the free body diagram or shear diagram or moment diagram. So far so good? So this is how we will draw a free body diagram in the statically determinate analysis. So we get a cross section of Mn, and we assume there's like shear and moment, and we can solve for the shear force and bending moment, like on the rest of the rod. So there's another important part. It's a sign convention. So as I said in earlier, the most important part of this course is we have to know where is positive and what is negative. Or you can define your own, this is definitely fine, but you have to keep in mind what system are you using. So like in the textbook you use, they define positive as this kind of shear. So it's basically, you can think that it is clockwise, going clockwise, like from the top and going down, going up. So when you see these kinds of internal force, this means it is positive. And for moment, in this textbook they define this kind of situation as positive moment. So you will have to really keep in mind, this is very important, you have to memorize it, or you will get like the negative or positive sign wrong in the end of the calculation. So this is the basic idea of the relationship between the distributed load and the shear force, or the distributed load to the bending moment. So as we can see on the graph here, with the distributed load adding, there's like an increment of the shear and an increment of the moment, right? So by subtracting the shear right here and shear right here, we can know that it is the integrate of the distributed load, like along the x. And the bending moment is pretty much the same thing. It's integrated by the shear. So it means that when you double integrated a distributed for a load, and you will get the moment. So how about like there's like different forces relationship, like this is for distributed load, and this is for the concentrated load, and this is for the couple moment. So I would suggest you guys like at least memorize or get familiar with these kind of relationships. So far, so good. So for these kind of questions, like the distributed load relations, the diagram will look like this, right? Do you know how to draw it? Okay. Do I need to like demonstrate how to draw it?
Yeah, maybe.
So I'll first. So for these kinds of situations, the first part is to calculate. For me, I'll calculate the reaction force first. So the reaction force, it is QL divided by 2. So once you get the reaction force, what's the next step? When we are drawing a shear diagram. Anyone has some ideas?
Moment.
So in my case, when I get this kind of questions for shear diagram, if the reaction force on the left is positive, I'll directly draw a positive point right here. And for this case, this side, if we are adding back to 0, since it is equilibrium state, so it will somehow need to add same RB right here, right? The reaction force of B. So since it is uniform loading, you just have to. So for these kinds of questions, we can do it very easily by noticing it is a uniform load type of question. So once we calculate the reaction force from A and B by drawing a line from these 2 points, we can get the shear diagram. And for moment diagram, it's more even easier. So for this kind of question, we'll have to, calculate the peak of the moment. So how to calculate that is by calculating the area of this part. This is QL over 2. This is, so calculated area of the triangle is QL over 2 times
L over 2.
and the peak will equals to QL
QL squared.
right here. So it means from this area it provides the moment to grow to here. So since this part is a negative area, you know that it decrease, right? So it decrease right here. Think it's really easy, right? this is the concentrated load relationship. So you guys, let's draw this, okay? So the same concept. The first step, we find out what is the reaction force at A or B. Alright? So for RA, the reaction force at A equals what? For these kind of questions? Okay, let's do this in the old school way. We don't need to rush. So sigma f of x equals what?
0.
0, yeah. Sigma f of y,
But there's
no, so equals rx plus ry. Right?
Yeah.
Forget about this. I'm doing the force equivalent stuff, right? So this is a 2D problem. So we are missing what? We have f of x, f of y. We are missing moment, right? Moment. Sigma m. So we'll be calculating the moment on A. So it will be P times what? A. And then
Over
minus RB times L equals 0, right? Yeah, so from this part, we can calculate the RB equals PA over L. And from this part, keep in mind L equals A plus B, right?
Yeah.
So RA equals right? Since P B L plus A L, this part is 1. Right? So we got the reaction force, right? For the shear diagram, as we did it on the last type of question, PB over L is positive, right? It's positive. So when we start drawing, we'll plot point right here is PB over L. Then this part is also positive, right? So in the last part of it, we will have to add the reaction force back to 0. So it means this part is reaction force B. And it equals to PA over L. So this kind of question is different from the distributed load. In this part, there's no force changing, right? There's no extra force in it. So the change will be at the concentrated load. So assume the load is right here, and we minus P. We minus P. Minus P. We get a nice shear diagram. So maybe you will be wondering why PB over L minus P is equal to PA over L. It's because it is P Okay? This is P, right? Because it's A plus B divided by L is equals to 1. Right? So the moment diagram is also the same. We have to find out where's the peak point, right? The peak moment. So calculate the area of this frame. How do you calculate it? It is P times A times B over L, right? So maybe you will be wondering why this will be a triangle type for the moment. It is because I've been emphasized from the function, the moment is integrated by the shear, right? So in this part, B equals to constant. Okay, it's constant, right? So if we integrate the B dx, it will be Vx, right? So what is Vx? It will be a line, right? So line here, finish. So far so good? Am I teaching the same way as Professor Wu or no?
No.
Yours is faster.
So before we are heading to the moment part, anyone has any question? Because what I'm doing is the way, I mean, it is not really a theoretical way, but it contains the concept of the theoretical concept. So the meaning of the, so I'm explaining about why are there like straight lines here and like about the peak moment stuff. Yeah, so this is another example. So for the shear, we can see, maybe we can guess, like the function of the shear will be somehow something like this, right? Because this is the line. So by integrating the V, it will somehow have like the x squared, right? So since it is like going down, in the shear, the k maybe will be negative, right? Yeah. So by negative x squared and divided by 2, it will be somehow a square, a circle like, a semicircle, right? So this is why I say when we calculated the peak moment and we just draw a semicircle. Yeah. But there's another problem that when in your exams, the professor asks you to maybe ask you what is the moment right here, and you will have a problem. So this scale depends on you guys. You can use it or use the original scale that Professor Wu told you. You guys want to take a break? and maybe 10 minutes break, okay?
Do you love me? Who's that, bro? So fat. And
So, this will be final questions or types of chapter 4, and I will show you or I'll draw you some graphs to help you to master this kind of questions. So, anybody know how to draw the shared diagram of this kind of problem? No? Guys, give some effort. I'll be crying. I just told you guys. Yeah, for this kind of problem, there's like 3 concentrated load, right? So you can, like, it's free, so you can divide these kind of questions into, wait me for a sec. Yeah, actually, there's a free concentrated load, right? You can, like, put every load into a new beam and add it up like all 3 forces in every situation. So, by drawing this, and this, like the shear diagram, it will be look like, what's this? So this is the free shear diagram in per situation, right? Just add it up. Add it.
oh, okay, now this,
Got it?
the positive part is the
This is positive power, negative power, positive power, negative power, positive power.
firstly there is no negative part for the last one.
Positive power. Oh no. For this, because I draw it on the end. So
Oh.
so if that, it will be like this.
Small part. Oh,
Yeah.
oh, I see.
So just add a shear diagram up. It will be look like this. So it will be like, can we add in the moment diagram? Is it possible? My suggestions will be just calculate the area. You calculate the area, so you got this part. Or there's another way, just like cut the section and calculate the moment. Like this moment 1, moment 2, moment 3. So we will calculate in each section the moment part. We can directly know like this 3 part is M1, M2, and M3. And what is it look like? Since it is concentrated load. Sorry. So it will be like line, 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 line. Okay? So this is yeah.
Can we do the same like superposition trick given like there's different types of loads, concentrated, distributed?
Yeah.
We can still do the same thing, right?
Yeah, yeah. But my suggestion is that for shear diagram, please use that, the superposition
Yeah.
way. And for the moment, I will suggest if you are really familiar to how the line will look like, you will have to calculate.
Okay.
Yeah, because when you are, just like we are saying, if the moment looks like this, and moment looks like this,
Oh.
when we are adding, how we were adding it, right? So I will suggest you guys, when you are doing this kind of problem, please calculate at least a moment. But I mean, when you calculate a moment, you'll get a force. So it might be a way for you guys to examine the answer is right or wrong, right? So can anyone tell me like how Professor Wu taught you guys, like what's the way?
Cross sections.
Cross sections, right?
Yeah.
Cross sections? So we're in the,
This one.
yeah.
Cross sections. You divide this one.
Ah, yeah.
Then you get the shear and the moment. Say cross sections.
Oh, cross section. Yeah, I believe Professor Wu's way is first calculate every moment and shear in every section. When like in here, and here, right? Like where the force or load changes. And you will get like the moment and the shear in this kind of places, right? But I think Professor Wu's way will be pretty much a good way for you guys to, I mean, once, if in the exam, Professor Wu would like to ask you guys like, oh, I would like to know the moments right here, then you will be struggled if we do it in my way, right? Because you're not sure, is it really in linear or it is a curve? So when it is a curve-like moment diagram, you can't really do it in my way. Unless it is a question to ask you how to draw the shear moment diagram. But I believe if you don't do the right procedures that Professor Wu taught in class, I think there will be some points minus due to, I mean, less of some functions or integrated stuff. So you will have to consider, is it really a need to use this kind of convenient way? So let me help you guys more. Like, how many people will see the record?
28.
8?
28.
28.
Yeah.
You are recording for 28 people.
Yeah, that's a whole year. A whole
Not 20.
How young are you?
Oh my God.
25.
25.
25.
Oh.
A whole sophomore is 25.
Oh, so you are like 1, 2, 3, 4, 5. So like leg of 10 people, right?
The rest of it have
I think
class.
it's 5 more
Or
people.
maybe doesn't want to come.
5 to 6 more people.
Ah, yeah, 5 or 6 more people.
Yeah.
David.
Huh?
David.
David. Budi. Budi.
I'm thinking about not to record what I'm writing right now.
Oh.
Wow.
So you can send the notes to your friends, but don't record it.
Okay.
Okay.
Okay? And what is the deflection? It is the main part of the chapter 5. So basically, I think this is more harder than previous chapter because it combines the concept of chapter 1 and chapter 4. Yeah, so you have to know what's the stress-strain relation, what is it, and know the basic definition of what is deflection, and really get into about drawing the curve or the coordinate axis. So I just draw this. I didn't draw this, right? Oh no, I didn't draw this. Sorry. The pure bending. This is the chapter 4. Okay. The case I drew is the moment are all in the same direction. So in this case, this is like the moment diagram of this situation. And there's another cases. This is the moment diagram of this non-uniform bending. You guys are familiar with this, right? I mean, did Professor Wu specifically talk about this kind of diagram? No? No. Okay. This is a concept of how the concentrated load affects the moment diagram. So it is the moment diagram of this kind of situation. And next, we have to define what's the curvature of a beam. I think this should be in your lecture, right?
Yes.
Yeah.
So keep in mind, there's like the center. Where's the center? Like right here, and the radius, and the angles theta right here, and the ds. So, anyone know how to calculate ds? The differential segment length? How to calculate? I believe Professor Wu have told you guys, right? It's the radius times the d theta, right? So this is the basic of the curvature. What is a curvature? So this is not only for a beam. It's for many other engineering stuff. Also use the same definition. So for the curvature, just as I say, how to calculate, can I, wait me for a sec. You guys see? Yeah. So, this is condition of small deflections. This is the assumption. So it doesn't really work when it is a really large deflection. So when for conditions like this, when d theta over dx will be what is it, kappa?
Kappa.
Yes, it will be kappa. So another thing is that we have to make sure, or we have to define where where is positive and where is negative. So when the concave bend upward, it means that the point right here, the center right here is above the beam and it is positive, and where the concave bend downward and the center is below the beam will be negative. So you will have to keep in mind what's the definition. It will be pretty much the most important part of the calculation. So one more new things in this chapter is about the neutral surface. And the definition is that maybe the surface where the line doesn't change in this. So like this, if we assume this surface is a neutral surface, then it means that in the upper and the lower part, the length will be changed, but in this part, the length will not change. Yeah. And one more thing is that why we did the chapter 1 review is about the strain. So the sorry, excuse me. So the strain of the curvature is also a relation with the y. So you can see. So if negative kappa y, negative kappa times y will equals negative y divided by this part. So it will be the definition of the epsilon x. So that's the longitudinal strain. So when it comes to the normal stresses in beams, there's another definition. So when you assume the material is linear elastic, so by the Hooke law that I mentioned in chapter 1, sigma equals E times epsilon. Stress equals E times strain, right? So we got strain right here. When we times E, Young's modulus, it will equals stress. So far so good? This is a part where you think it's easy, but it is a part you have to keep in mind through whole the chapter, because it will be the basic concept of every calculation. So for the neutral axis, where can we find it? So we are first find the centroid of the shape, right? The cross section, right? So I believe I have reviewed how to calculate the centroid of the shape. So it's the same method. So far we've been through the strains, the stress, and the location of the neutral axis. So we're moving into the flexure formula. So it is really important that memorizing this. Do you know how to memorize this? You can think it is mind divided by I, right? So
Mind divided by.
yeah, it is really easy to memorize. So this is based on the previous slides, like sigma equals to right here, the kappa right here, okay, right here. So substituting the normal stresses and the moment of inertia, you will get this equation right here. So when we are getting back, what is the normal stress? And we substitute all this into the original equation that I mentioned before, you will get this flexure formula. So keep in mind, this is really important, just like I say in chapter 2, the PL over EA. This is like the main concept of this chapter. So, what is Y? Do you know what the... Oh, one more thing is that when it is positive bending moment, the tensile, when Y is negative. These two lines, please know what is it talking about. It's really important. So, we are talking about the upper part of the neutral axis and the lower part of the neutral axis. You can see right here into these two graphs. This part is the positive bending moment. So you can see if it bends right here positive, this part will be compressive, right? It's easy to imagine. So this part will be the tensile part. So in this positive bending moment situation, the upper part of the neutral axis will be the compressive stress. The lower part will be the tensile stress. So in the other way, the negative bending moment is clockwise, right? So this part of the beam will be compressive, and this part will be tensile stress. So another model is like the definition of the section modeling. So it's basically they somehow quantify the geometry that relates to the cross section part with like a moment of inertia and the distance from the neutral plane. I mean, distance from the neutral plane. So this is like a definition only. So you have to memorize in your way. So you can see this is like my vs to over I, right? So when my over I, so I will be in the lower part and y or c will be the upper part. So it will also mean the stress is equal to moment divided out the section moduly, right? So this is you guys. The professor will talk how to design a beam. How to design? No? Yes? No? Okay, I believe maybe or maybe not. So this part is like when you take the course of RC design. It is like the concrete and the rebar stuff in the civil engineering. So yeah, so you're designing the beam for bending stress. There's like this equation, like the section modulus, so it equals to 0.5 AH. This is somehow a design method. So this is we are talking about the normal stress. I mean the pure bending, right? The bending stuff, the positive bending and negative bending. So we talk about the force, the moment to this section, right? Now we are talking about the shear. Okay? So this is the equation of the shear stress. So the equation of the shear formula is VQ over IB. And I is the moment of inertia, the B is the width of the location, the beam's width. And the B, of course, is shear, and the Q is the first moment. So I think you guys maybe only struggle on how to calculate the moment of inertia, right? Or maybe the Q. The shear and the width, you got it like very fast. So what struggle you most is the moment of inertia, right?
This isn't included in our.
What?
We don't know.
Louder, a bit louder.
It
Sorry.
isn't included in our chapter 5. The professor didn't teach us this.
Didn't talk about this?
Yeah.
No.
So what is it?
It was just until moment, until my over I.
Yeah.
Only MY over?
Yeah.
Yeah.
So
It's
did
like-
Professor finish chapter 5?
Yeah.
5
Let me check for the lecture because this is from the textbook. So
This is the syllabus. You just follow the syllabus.
no. I know this is
Just 5.1, 5.2, 5.3, 5.4.
Okay. Can you share me the lectures notes?
Yes.
7, 5.5, 5.6.
Example.
So by the area will be the stress like causes by the force. So we will calculate the stress like induced by the moment. So you can see the force right here causes stress, and moment also causes stress. But if we skip the shear part, because shear doesn't cause normal stress, so you can see the equation will be N over A minus My over I. Since there's like different, this is compressed, this is tensile, right? And this is when there's like eccentric load. This is the situation. This is also the same concept. It's like where the axial force over the area minus or add the moment times the y and over I. Okay, so far so good. The concept is always simple. So keep in mind the concept isn't really complicated, but where will we get the N, where we get the A, is what we will have to dig in the question and find out where is the factors that we need. So how about this? No?
No holes.
No, this as well.
No, just... Okay, then let's go through this summary and we'll call it a day. So, I think this page is in Professor Wu's lecture, right? Like the strain equals kappa, negative kappa y, and kappa equals m over ei, and stress equals to negative my over I, right? And this shear part, I think you guys will have to make sure if it's not, if it's not, I think if you guys are sure, then we will skip it. And I think today we finish chapter 1 to chapter 5, and then got chapter 3. So I think the most important part is not like how will you guys deal with this kind of problem. It's like when you get the basic concept and how will you find the procedure to solve every problem. So I think that's for today's lecture.
Can you share the PPT?
What?
Can you share the PPT?
Share the PPT?
Your PPT, you just presented to us.